Okay, so one of the things that we find from doing some basic experiments with static electricity is that we have to conclude that there are two types of charge. Okay. Now, the reason why we have to conclude that there are two types of charge is actually pretty subtle. It isn't a one sentence explanation. You have to go through a few steps to get to that point. I want to emphasize that these two types of charge are not. They're not. There's nothing fundamentally positive and negative about them. We call them plus and minus, or positive and negative. But that's really just a shorthand. We could have called them, A and B. We could have called them 1 and 2. We could have called them red and green. We could have come up with any names at all that we wanted for these. And historically, people chose positive and negative. But it would not have to be, and there's nothing inherently opposite even about the two types of charge. Okay, so if you identify some positive charge and some negative charge, then what you'll find is that if you bring two positive charges together, or if you bring two negative charges together, then they repel. Meanwhile, if you have a positive and a negative charge near each other, they will attract. Okay, and again, that's just based on the model that we have. There's no inherent reason why things that are the same kind should repel or opposite kinds should attract. We'll even see later in this quarter that there are some cases where the same kind attract and opposite repel for a different phenomenon than electrostatics. So this is just observations that we've made of the phenomena. Another observation that is fairly clear from some simple experiments is that the force between two objects decreases with distance. Okay, so if you bring two charged objects close together, then there's a strong force between them. If you bring them further apart, the force gets weaker and weaker. Be careful not to mix up force and charge. So force is the actual push or pull between objects, while the charge is this invisible property of materials that we infer is present and that we believe is causing that force to occur. But we don't ever directly see the charge. What we see directly, or what we directly experience, is the force. You can also find that there are sort of two different classes of materials. So for some materials, the charges on those materials will move around freely. And for some other materials, the charges stay where you put them. Okay, and so for materials where charges can move around freely, we call those conductors. For materials where the charges don't move, we call those insulators. Another observation, and this one is a little peculiar, is that uncharged objects are attracted to charged ones. So in the lab, the uncharged objects are the little bits of paper, and you'll find that those are attracted to an object that is charged. But we're going to explore in an upcoming video in a little more detail why that occurs. Okay. Another fact about charges that can be determined from experiment is that charge is conserved. Okay, so we don't ever create one kind of charge. When you are, say, rubbing a balloon on your hair, You're not creating charge on the balloon. What you're doing is transferring charge from your hair to the balloon, or transferring charge from the balloon to your hair. But you're not creating any. It just kind of seems like you're creating some because you've moved some charge. We also conclude from experiments that matter is not just sometimes charged and sometimes uncharged, but it is actually built up of a huge amount of both kinds of charge, which largely cancel. So matter has lots of positive and negative charges. Okay, so from a more modern view, we know that matter is built up out of positively charged nuclei and negatively charged electrons. So in fact, all of the matter is positive and negative charges. There aren't any of the parts that are entirely neutral unless you bring together positive and negative charges. And finally, the last part of the model, and this is not something that you are able to see with the experiments that we've done, but there are some other experiments that can be done that show that charge is quantized. Okay, so what does that mean? Well, the amount of charge that an electron has is the smallest amount of charge that we ever observe in nature. Okay, so you can have 1 electron's worth of charge, or 2 electrons worth, or 17, or 1.3 million, but you never have a half of an electron of charge, or like 3.7 electrons worth of charge. You can only get that amount. And there are positive amounts from adding up protons and negative amounts from electrons, but you never see some other amount than an integer amount of charge. If you have studied into some particle physics a little bit, you might be saying, wait a minute, I've heard about some particles with 1/3 charge. And that is true. There are some particles that we believe have a 1/3 or 2/3 charge. So I would counter with two things. One is those have never been observed in isolation. So we only ever see them in combinations that come out to integer amounts of charge. And then also, even if the basic quantized amount of charge was 1/3 of an electron's charge, that's still a basic quantized amount. It's just a slightly smaller quantized amount. And you would never see like, a half of 1/3 or something like that. It would always be multiples of 1/3.